Okay, so good morning everyone and welcome to the 14th in the LimitState webinar series for 2015. Today's webinar is slope stability using LimitStateGEO, and we'll introduce you to the technology behind our geotechnical analysis software LimitStateGEO, and also demonstrate how the software can be used for a number of different situations. This main section of the webinar will run until approximately 10 AM UK time and will include 5 to 10 minutes at the end for questions. These can be posted any time via the chat facility that is present in the webinar interface in front of you. We'll try and answer as many questions as we can, but sometimes this isn't always possible, so apologies in advance if we're unable to get to yours. We will, however, follow up any unanswered questions after the webinar is finished. Now, we've got a mixed audience today. Some of you will have used LimitStateGEO before, some of you will be new to it. But if you do have any specific questions regarding the software, which may require some consideration or time, please contact us outside the webinar via info@limitstate.com, and we'll be happy to answer any of these questions in detail for you. Now, back to today's webinar. My aim today is to show you how LimitStateGEO can be used to solve slope stability problems, how it differs from other methods, and how to model a number of specific scenarios. To this end, I'll primarily be using the software directly to illustrate the key points, but I'll make use of a few slides at the beginning and end for an introduction and summary. As this is a problem-specific webinar, I'll focus on how to use the software to solve slope stability problems, and therefore I might skip over some of the details of how to use the software, but hopefully the process should be clear. Okay, I think just to start, I think it's useful to give a little bit of context to the software and to the company LimitState. So the University of Sheffield has been conducting research into limit state analysis and design and the use of optimization in civil engineering for almost 2 decades now. LimitState itself was spun out from the university in 2006 with the aim of making this research available to industry. Now, of course, as industry users, you want not only powerful tools, but also ease of use and full support. And that's what LimitState can provide on top of the academic research tools. The company also has sophisticated testing systems in place, which means every time the software is changed, almost 1,000 tests are automatically run to make sure that it carries on doing what it's supposed to do. At present, the company has 3 products available: LimitState Ring for Masonry Arch Analysis, LimitStateGEO, subject of today's webinar, and LimitState Slab for concrete slab analysis. And the software is used by many contractors and consultants, large and small, across the world in over 30 countries worldwide. In terms of LimitStateGEO itself, as you are probably aware, the software is a general purpose ultimate limit state software and can determine the collapse state for any problem geometry. And as illustrated on this slide, we can model slopes, foundations, retaining walls, mixed problems, soil structure interaction, a whole range of different types of problems with the software. But today we're going to focus on slope stability analysis. So just a little bit of background about sort of classic methods that you may be familiar with or in textbooks. So we're going to look at 3 of these methods. First one is a translational slip or a planar slip. This generally, the theory only works for infinite slopes, but it's pretty straightforward. The factor of safety that we determine in this is effectively defined in terms of a factor on soil strength. So if we quote a factor of safety for a planar slip, we're talking about a factor on strength generally. We might look at undrained slopes and look at Taylor's slope stability analysis. This is technically an upper bound limit analysis approach for undrained slopes. And what is assumed is a circular arc slip surface. And based on that, the factor of safety on strength is worked out, averaged over the length of the slip surface. Final method, and perhaps the most commonly used one, is the method of slices. That has a fairly general applicability. It's what we call a limit equilibrium approach. The slip surface shape is assumed. It may not be kinematically compatible. Generally, in the method of slices, the problem is not statically determinate, therefore we have to make assumptions about interslice forces, etc. But the result that we get out is generally expressed or can be interpreted as a factor of safety on strength averaged over the length of the slip surface. So in all three cases, we're talking about a factor on soil strength. And this, as I've said, is probably the most popular method of general purpose slope stability analysis, originally developed for hand calculations and now automated in a number of software packages. If we look at the available geotechnical analysis software and where LimitStateGEO sits in that, and in the context of slopes in particular, on this diagram on the top left, we have the sort of software that is perhaps based on what were hand analysis solutions like the method of slices. So that's automating something that was, albeit a fairly tedious hand calculation, and has a long history to it. Those sorts of programs can solve very specific types of problems that generally do a good job, but they're not particularly flexible. If you want to solve something more complicated or kind of hybrid problem, then you're going to move to nonlinear finite element software. That can deal with very complex geometry, very complex soil behavior, but requires a lot more data and a lot more expertise to use. And what we feel is there's a gap between these two, which is filled by computational limit analysis, or what we call rigid plastic analysis. And that's what this software LimitStateGEO provides. Essentially, it gives you the flexibility to model any geometry that finite elements give you, but it gives you the simplicity of traditional methods. Generally, the only parameters you require are cohesion, friction, and unit weight of soil. This sort of technique can be used not only for geotechnical problems. As with our other products, we can apply the same technology to masonry arch bridges or to yield line analysis in concrete slabs. Now, in terms of the method that is used in LimitStateGEO, we are using limit analysis, and that is a procedure which is concerned with finding the maximum load sustainable by a body or a structure, which is assumed not to deform prior to collapse, and they will deform at a constant load subsequently. So it's what we call a rigid plastic idealization. So in the graph on the right-hand side of this slide, the grey curve might be the typical response of your material, your soil, and we're basically idealizing it by that red line. And this is a classic sort of analysis procedure. It's been used in geotechnics for many, many decades and forms the backbone to many, many formulae that we use in geotechnics. Now, if you're familiar with limit analysis, there's some very nice theorems which are called the lower and upper bound theorems. That says that we could calculate a lower bound to a collapse load if we can find a solution that satisfies equilibrium and yield everywhere. And we can find an upper bound to the collapse load if we can find a mechanism of collapse that satisfies compatibility and work conditions. And the optimal upper bound will equal the optimal lower bound and will equal the true plasticity solution. So if we get our best possible upper bound or our best possible lower bound, we should get the exact solution. And that's the sort of basis of the software LimitStateGEO. So what it actually employs is an upper bound limit analysis approach using discontinuity layout optimization. It's a new, well, relatively new numerical technique, which I'll explain shortly. It doesn't require any additional assumptions, so there's no assumptions as in other slope stability software of entry-exit points, interslice force assumptions, etc. And it can provide analysis that is a factor on strength applied to the whole soil domain, which is the sort of answer you'd want for slope stability. And it automatically determines the critical failure mechanism. So in the mechanism illustrated here, you can see that it's certainly not a circular slip surface. Up in the top right, we've got a curved slip surface which then meets an interface between two strata. The slip surface then runs down that strata. When it gets to a retaining wall that's been constructed in the slope, it has to dive down into the stronger strata to get under the wall and up to the sort of excavation that's been made into the slope. and the software will find that critical mechanism directly without any requirement to tell it where to look or how to deal with that. Okay, so how does that the software actually work? Well, the key enabling technology is what we call DLO, or discontinuity layout optimization, and it can be used to provide rigorous upper bound plasticity solutions, which are very accurate and very close to the true solution. It's a rapid and direct means of analyzing the collapse state, and it was the outcome of a 5-year research project at the University of Sheffield. Key publication appeared in the Proceedings of the Royal Society in 2007, but I can explain the whole process in 4 diagrams. Obviously, the mathematics behind it's a bit more complicated. So if we assume we've got a domain here with a load on the surface and fixed boundaries to the bottom and to the left, what we do is we populate the domain with nodes. So this is not an element-based method, it's a nodal and discontinuity-based method. We then connect every node to every other node with a potential discontinuity. So we have 12 nodes here. So we have 12 times 11 over 2, about 66 connections there. And we set the problem up as an optimization problem, which the software then takes those potential nodes and or slip lines and picks out those that give the critical collapse mechanism, i.e. the one that generates or dissipates the least energy. And so in this particular very simple problem, we get a 2-wedge sliding block mechanism involving about 6 slip lines out of the original 66. Now normally we're solving with problems with, say, 1,000 nodes, that's 1 million potential slip lines, and out of that the software will pick the critical collapse mechanism in a matter of seconds, as we'll see shortly. So it turns out that that type of problem is a simple linear optimization problem. It's easy to solve with modern state-of-the-art optimization solvers. And once we've solved the problem, we can identify the blocks between the discontinuities and animate them to aid interpretation. So here we've got a slip mechanism and a 2-layer slope, and it's been animated to show the sort of deformation pattern. A key point is that the accuracy of solution depends on the number of nodes you have, because that gives the software determines the number of slip lines that it can choose the critical mechanism from. So the more you put in, the bigger range of nodes or discontinuities the software has to generate a slip line mechanism from. Okay, well that's enough sort of introduction. Let's move on to using the software and just illustrate how that works. So I'll start up the software. So this is the standard layout. You'll see a number of buttons on the top and down the left-hand side, and some other sub-windows. I'll describe these as we go along. To start a new project, you just click the button New, and you get a choice of projects. Software comes, you can start with empty and draw your own geometry, but the software also has quick build wizards to generate standard geometries, which can be modified later. We'll use a slope stability one. So you get a wizard, and as you go through this, I'm going to go through this fairly quickly. You get asked, so you can change the geometry of the slope. I'm going to accept the defaults. You can add a water table if you wish. You can define the properties of the soil in the slope, so you can define an undrained shear strength and also its unit weight, and also, if you wish, drain parameters. In this particular wizard, you can put a surcharge. We'll leave that at 0 for the moment. You can define partial factors. We'll leave those all as 1, but you can enter Eurocode partial factors. And we can define an analysis type and a nodal density. I'll come back to those shortly. So I'll just click Finish, and then we have a very simple geometry. very steep slope and it's an undrained material. Anything I click on in the software, its properties will appear in the property editor on the right. So if I click on here on this block here, the properties of this solid appear on the right, and it tells me what soil I've got in there. And I've got a soil which is an always undrained soil there and has an undrained shear strength of 50 kPa in this case. If I want to solve the problem, I've got a choice of solving it using what we call factor load or factor strength modes. Factor load is a mode that we use. We have to specify a particular load in the system, and the software will tell us how much bigger that load has to be to cause collapse. Factor strength is the mode that we're most interested in for slope stability, and the software will simply tell us how much the strength of the soil has to be reduced to cause collapse, and in essence that's a factor of safety on strength, which is a typical number you want from slope stability analysis. So I click solve, and in a few seconds it comes up with a critical collapse mechanism, and that's very similar in form to what you'd see from a Taylor slope stability analysis, although in the Taylor method it's a simple slip circle, and we get an adequacy on strength of 2.47 down here. So that basically means that we need to reduce the strength of the soil by a factor of 2.47 in order to get collapse. You see we get the animation which shows us the type of failure, and we'll look at some comparisons with Taylor's analysis later between that and DLO. Just to clarify what this factor of strength is doing, if I take this soil material, if I reduce the strength by a factor of 2.47, or I'll do it by 2.5, so if I reduce it to 20 and reanalyze, then I should get an adequacy factor of 1, or a factor on strength of 1. Which is what the software, just under 1, and that's saying we don't really need to change the strength. This system is on the point of collapse. So I'm going to just click undo, which will revert that change that I made and return me back to 50 kPa for the strength of the soil. Now, software, very interactive. You can play around with the geometry any way you like. I can click on a point up there and drag it sideways and look at the analysis of a somewhat shallower slope. So if I click solve again, I now get a slightly different mechanism. The mechanism is much larger. It's starting, the base of it's starting to go below the level of the toe, and the adequacy on strength has gone up to 2.73. So the factor of safety on strength is higher, as we'd expect for a shallow slope. And if I move that back further, I'll start to get a mechanism which goes below the toe. And again, the adequacy on strength, or factor on strength, will go up. In this case, it looks like it's coming out at 3.06. You'll see that the mechanism actually intersects a boundary here, so technically that's not valid if there is really soil behind. And it's very easy to click on the boundary and move it out and resolve. Now, for those of you familiar with this type of analysis, you'll realize we're onto a sort of road to nowhere here. I can keep pulling these boundaries out forever, and for this type of, for slopes that are shallower than this angle or this angle, that the actual critical mechanism is effectively of infinite size, but the factor on safety doesn't change that much. So if I kept pulling those boundaries out, the mechanism would just grow and grow, and that's what you see from the Taylor analysis also. Now, just to continue, say a little bit about nodal density. In this case, we've got a medium which basically says use 500 nodes, and you can see that that kind of analysis is fairly quick. And we recommend generally using medium or coarse for sort of interactive use, trying to explore what parameters control the failure and so on. And that's what I'll use in this webinar, but we can increase that number to fine or very fine. Fine is 1,000 nodes. Or you can actually type in a number there. You don't have to stick to these numbers exactly. And what you'll find is if you solve there, that the solution will take a little longer to get there, but it will be more accurate. And what we recommend is when you've come up with your final refined model that you just increase the number of nodes and just check that the factor on strength that you're getting from the solution doesn't change significantly as you've upped the nodes. So this, we've got 2.81 for this one. The previous solution was 2.82. So in fact, there's almost no change there. For this particular problem, that number of nodes is going to be perfectly adequate to give us an accurate solution. Okay, so that's a simple undrained slope, which we could compare to Taylor's slip method, and we'll look at that a little bit later. What I'll do now is do a comparison with that method of slices solution. So I've constructed a model that replicates an example from the textbook by Whitlow. So he gave a few examples of method of slices, and it's a slope of this angle. If I click on this body here, the soil that was analysed in the book had a C' of 5 and a phi of 30 and a unit weight of 20. If I just click solve, we'll solve that. And the solution in Whitlow's book using the method of slices, using Bishop's simplified method, came out as 1.6. And here in this software, we've got 1.63. So very comparable. Clearly, the method of slices doesn't have a formal theoretical basis or status, I should say. But of course, it has been widely used and verified. So we get a very close comparison there. So that's the method of slices. We'll come back to that a little later, but I'd also like to look at planar slides. So I'm going to open up another file. So this is looking at a planar soil. So this soil here has simply got a C' of 0 of phi of 30, unit weight of 19.5. I've actually just put some rock in this area here, just to keep us focused on the failure at the surface. This is what we expect for this problem. We're going to expect a shallow slide. Now the angle of this slope has actually been drawn to be an angle of 35 degrees, while the slope angle is 30. So technically that slope is unstable as it is. It cannot stand up at that angle. It should just fail. And if we tried to find a solution in the software, initially it will just say it fails. But if I click the factor of safety, factor of strength solution, what it will do is it will find the factor which makes this system just fail, and it's 0.838, and that turns out to be very close to the actual ratio. The actual factor of safety on strength for this problem will be tan 30 over tan 35, which is 0.823. Here we get 0.838, so that's about 2% out. Now that's partly because this isn't an infinite slope that we're modelling, and the factor of safety, that simple ratio of the tan 30 over tan 35, is for an infinite slope. You'll notice that it doesn't actually show a mechanism, and that's because technically the slope is either stable or it's unstable. If phi is greater than the slope angle, it's stable. If it's less than the slope angle, it's unstable, and there's only one point in between. And that makes it the software can't actually identify a mechanism. It can just say it's stable or unstable. If you want to see the mechanism or get an idea of it, it's quite useful just to put in a very small C', and that gives you enough capacity that the software can then identify a mechanism and a somewhat different factor on strength. So if we add that there, you can see the software is trying to produce a mechanism using the nodes that it has. It's a very, very flat mechanism, as planar as it can get it, but still intersecting the toe and the crest of the slope. We get a factor of 0.861, so that's a bit higher. That's about 4% out, but we've added a 0.1 cohesion to the problem. And you'll see that when we animate it, we get this gap forming. Now that's perfectly standard. This is software solving the problem using limit analysis, which is a rigorous plasticity theory, And in plasticity theory, the friction in the soil is modeled using dilation. And so the animation, as this soil slides, it's modeling the blocks moving apart, and that's just basically modeling dilation. That gap is basically representing dilation. Now, I slightly cheated with this model because by default, the software adds a cohesion of 0.1 to any frictional soil that has a 0 cohesion or as pure friction only when you're in a factor strength mode because of this issue that you cannot find the mechanism. You can turn that on and off. If you go to Analysis Options, you get Factor Strength, click Advanced. There's a setting there. So at the moment, I've actually set this up deliberately to be 0, but the default setting for here is 0.1. And so when you're doing a factor strength analysis, it will add an artificial cohesion of 0.1 if, or set the value to 0.1 if it's less than 0.1 for any material. Okay, so I'll cancel that. Okay, so that's a brief run through the sort of three failure modes, three classic sort of failure modes. We'll just revert back to the presentation briefly and just talk a bit about verification. Now, I've shown that the software is capable of solving a wide range of geotechnical problems, whether it's retaining walls, slopes, foundations, etc. And clearly, you want to be confident that it actually does what it says it does and does it accurately. So, as I said, every time the software is changed, we run about 1,000 tests internally to make sure it does what it should be doing. We've made about 100 of these available online. These are what we call our verification tests, where we've scoured the literature for solutions to limit analysis or collapse problems, got the results from the textbooks or the journal papers, and then run exactly the same problem in the software. And then we've posted that up there. So this is an example of an undrained slope stability, 60-degree slope, rigid below the level of the toe. Benchmark from the literature, that would be a Taylor's analysis or a similar 5.25 software. I think using a coarse, so not that many nodes, 5.35, so basically an error of 2%. And if you go to the website, this web address, you can find a whole range of verifications across a whole range of different problem types. I mentioned Taylor's stability charts, so I've just picked out two curves from Taylor's charts, which are these dashed line and the solid line, and the symbols here, basically the software results. So you can see they match very closely with Taylor's analysis. Finally, we've put together a bibliography of all the papers. There's about 40 journal papers published to date that discuss or use DLO method in analysis, covering all subjects from foundations, slope stability, retaining walls, seismic problems, etc. And I've put this will actually be available on the website very shortly, but I've just captured an extract here. So there's 3 papers there on slope stability, where it's been used for slope stability, that are published in international journals. Okay, so that's a brief look at verification. Now we'll go and look at some slightly more complicated slope problems. So we'll do another demonstration. And we'll return back to that this slope. So this was the Whitlow example that we compared with the method of slices. And if I just solve that again, we can see the mechanism and remind ourselves that we got an answer of 1.63. Now, if we want to apply safety factors to that, so we could sort of say that's a factor of safety of 1.63 on strength for the whole slope, be happy with that. But if we want to apply that to Eurocode 7, then we could use a scenario manager, and that allows us to set factors on unfavorable loads in the system, favorable loads, and material properties, C-tan, phi, and Cu. And we can set those to any value we want. Just to illustrate effectively what we're doing, if I click on user here, I change these values to 1.63. If I pre-factor C dashed and tan phi dashed by 1.63, so the software will pre-factor the properties that way, then we should get a result, an adequacy factor of 1 or a factor and strength of 1, which we do here. So what we get here is effectively the extra capacity in the soil over and above what has been reduced by the partial factors. So as long as this number is bigger than 1 and we've applied factors previously, then the system is stable. Now, of course, we're more likely to want to do this for Eurocode. Now, you can type in the Eurocode values, but they are actually built in. So if I click on there, you'll see, if you're familiar with the Eurocode values, we'll pick DA1/2, which is the one that's most appropriate for slope stability. And we see the various factors there. And in particular, we're factoring C dashed and tan phi dashed by 1.25. So if I solve again, I will get a slightly different answer. And this one comes out as, I think it comes out as 1.3 when we get there. Yep. So we get an answer of 1.3. And as I said, that's an additional factor of safety on strength over and above given by the Eurocode factoring. So that 1.3, if we take 1.3 and multiply it by 1.25, we'll get back to our original 1.63. And for the Eurocode, it's only necessary to show that the adequacy factor is bigger than 1 to satisfy the requirement that actions are less than resistances. And the nice thing about material factoring in numerical methods is that you can let the method find the critical mechanism, and that's hard to do with resistance factoring. So use the power of the software to find the critical mechanism with those factors pre-applied. Now maybe we want to have a load in the problem. Maybe there's a surface surcharge up here. If I click on the boundary, its properties appear on the right. I can apply loads to it. Let us say we want to apply a variable load of 5 kPa. And we should check that that's unfavorable. So it's set to unfavorable. I could set it to favorable or neutral. Neutral isn't a Eurocode setting, but it's put there in the software to say don't apply any factors at all. But we want it to be unfavorable. And now if I solve the problem, that load of 5 will be pre-factored by the unfavorable variable factor of 1.3. So I can run that through the software, solve that. But it will turn out actually that that has very little influence because the stability of the slope is primarily controlled by the weight of the soil in the slope, and that surcharge is fairly negligible in comparison. So I think we get an answer of 1.29, so it's not really destabilized things too much. Now, of course, water is usually quite a big issue in slope stability problems, so we can model that. I haven't got time to look at that in detail, but we'll look at a very simple case. So the simplest one is to just draw in a water table. So I can start here, draw in a water table there. So we have a very simple phreatic surface. And I click solve. And while I've drawn that in by hand, it's very easy to actually set the coordinates to specific values. So we'll let that run through, and we get an adequacy factor, basically a factor on strength of 1.1. So that's having applied the Eurocode factors, but that has dropped from that 1.3 or 1.29 before. So that water has had a fairly significant effect. If the water table dropped, I could just drag that water table down and resolve. That water table is now deeper than I think the original collapse mechanism and probably won't affect things. Software is just iterating to get to a factor on strength solution. It's actually factor load mode is quicker, but the factor on strength you actually have to iterate to get there, so it takes a little longer. But you can see that software is finding a mechanism that's above the water table, and we're back to our original 1.3 or 1.29. The reason it's changed slightly from 1.29 before is that by adding the water table, we've actually changed the distribution of the nodes in the problem, and that's caused this small change. Okay, I shall get rid of that water table. Now, sometimes you have an issue where you want to model a layered soil or a layered slope, so I could draw a line, for example, across the slope, and perhaps I've got a stratum below which is a different material. Now, you can define your own material properties, or there's some built-in ones here just for very sort of quick trial and error analysis. So I'm going to grab this firm clay and stick it on the lower layer. Now, just to recap, the top soil, has a C' of 5 and a phi of 30, and the soil below has a C' of 3 and a phi of 20, so it's weaker, so we should expect to get a lower margin of safety. So again, when we analyze this through, we actually get an adequacy of 0.895. Now that's less than 1. That means that this slope does not comply with design approach 1 combination 2. That number needs to be bigger than 1. It basically means that in the whole system, the soil strength needs to be increased by the reciprocal of 0.895 in order to make it just stable or just comply with the Eurocode factors. Now, if I undo, I can remove that. One other situation you might have is that actually you don't have layered soil, but you've got a pre-existing slip surface in the system that was the result of a previous landslide, and of course that might have a weaker strength. So as well as changing the properties of solid areas, we can change the properties of boundaries. And so what I'm going to do is basically put a very soft clay on that boundary just to make it weaker. Now, it may not be the right sort of material to put in there, but it will do for the purpose of the demonstration. So I can drag and drop materials from here. There's various ways of setting material properties, or if I click on there, I can click up here and click change and select the material I want. I'm going to stick with very soft clay. So now I've got a very thin, weaker surface, and then if I solve again, what I would expect to happen is that the software is going to say, okay, the critical mechanism is going to slide along that boundary, and we're down at 0.96, so still below 1 and still below that 1.3 that we had before. And just while I've got that one up, the software also generates reports. So if we click Analysis Report, you can choose what elements to include. I'm going to accept all of those, and you get a report, tells you about the analysis, the adequacy factor over here, diagram of the mechanism, partial factor sets, all the loads, geometry, etc., material properties, partial factors that are used, etc., etc. So all there, all can be output as PDF or an RTF, and you can edit the RTF freely to adapt it to your purposes. Now, one issue that quite often comes up is if you've imported the geometry of your slope problem from a CAD file, and you can do that quite easily. We have an option which is basically File, Import Geometry, and you can import from DXF. I won't do that. I'll just pull up a file that illustrates things. So you might have pulled up something like that, and quite often in those you get things like this, where there's a short, very steep part, which may be real or maybe just due to the survey. And if it's real, quite probably it's stable because of unsaturation or locally stronger. But the software will always seek out the critical failure mechanism. So if I click Solve here, basically this slope is exactly the same as the one we've seen before, but just with this little step. So if I click solve, what it will do is just says, well, that very steep bit will fail. That's a critical failure mechanism. We get a tiny little failure just here. Now, of course, you may not want that because you might say, well, that's not really what I'm interested in. I'm interested in a bigger failure. So there are two ways around that. One is to just flatten that part of the slope and get it back to the same gradient as the rest of the slope, or you can locally strengthen that, because of course in reality that must be locally stronger than we think it is, otherwise it would have collapsed. So what I'm going to do is just connect up these 2 points, and I can make that part of the material slightly stronger. So I'm going to take soil A. If I right click on that, I can duplicate it. I've got a copy there, and I'm just going to increase its C dash from 1 to 3 in this particular problem. And I'll just change it color so we can see what it is. And if I just drag and drop that into there, that means that we've now got a slightly stronger body up there. So if I click solve now, that's now strong enough to not to fail locally, and the software will revert back to finding a large scale slip mechanism. And in this particular problem, it's 1.28, so it's slightly different from that previous example. Now, if you've got a slope which is not stable or doesn't have the required factor of safety, then you might well want to look at improving the slope and increasing its stability. And of course, you can do that by various ways. We'll look at another example. Revert back to an undrained slope. So here we've got a soil A which is always undrained and has a CU of 30 and a weight of 20. If I solve that problem, I get a deep failure and an adequacy on strength of 1.75. So that might well be perfectly adequate, but if you want to improve that, we could perhaps add a berm, and I could use this tool here, polygon draw tool, and perhaps I would start here at a fairly shallow angle. I need to draw the whole polygon out, and I can take a dense sand. Let's say, for the purpose of illustration, we make that out of a dense sand. So now I've loaded the toe. If I click solve, I get a similar mechanism, but we've kind of suppressed the original one, and the adequacy or the factor of safety on strength has gone up to 2.04, whereas before it's 1.75. So that might be sufficient. We'll now look at another alternative. So I'm going to revert back to this example. So this is a drained slope, the original Whitlow example that we looked at, and where we got a factor on strength of 1.63. Now we could say, well, maybe we could add a retaining wall in there, or something that represents a row of piles to stabilize that slope. And we could do that quite easily if we draw a line. Say I want to put one in halfway up the slope or part way up the slope. Draw a line right down there, and then add a vertex using this tool here, maybe at this level. Let's put it down here. And I can model a sheet pile wall. So in the software we have, if I create a new material, we have what's called an engineered element, which is something that we can use to model sheet pile walls or soil nails or geotextiles. So I'm going to pick a rigid sheet pile wall, which is fairly basic. All the properties are set by default. So I just click OK. And this new material here, perhaps I'll call it sheet pile. For clarity, I can drag and drop that onto there, and that will actually behave as a rigid inclusion in the soil. So if I now click solve, the slip mechanism is going to have to either avoid that or go around it. So in this case, it's deep enough that it's saying, I can only fail at the top, and the factor in safety and strength has gone up to 1.88, whereas before it was 1.63. If that becomes too short, then clearly it's not going to have any influence, and the failure mechanism will just go around it, and we'll get a number pretty close to 1.63 as before. And if you have the long wall, then if you want, that might facilitate, if I draw a line there, excavation of material if you need somewhere to do some construction, and you can look at how that stability plays out in that particular case. So here that wall has given us stability of 1.78, so that's still higher than the original 1.63. So hopefully you can see it's quite easy to play around with the geometry and explore possibilities. What I'll do finally, just as we're nearing the end of the webinar, is if I just click undo and revert all of those changes, is we could look at slope reinforcement. Discussion of reinforcement is beyond the scope of this presentation, but I'll just show one example of adding a soil nail halfway up the slope. So again, it's a similar process. I'm going to click here and draw a line like that. I'm going to add a vertex about there, and I'm going to create a new material. Again, I'm going to use an engineered element, and this time it's going to be a soil nail, and I'm just going to use a rigid soil nail here. Now we enter in properties. I haven't got time to discuss these, but properties that represent the pull-out factor for the nail in terms of cohesion and friction in the soil, and a lateral factor, which I'm going to set to be very small, and click OK. I'm going to drag and drop that there. So effectively we've now got a soil nail in the problem, and what that should do is add a bit of strength to the system and increase the stability. So that in this particular mode, modelling a soil nail, the failure mechanism can pass through it, and what we've got is an adequacy and strength of 1.77, so it's gone up from 1.63, so it's had a reasonable effect. This graph that's appeared here actually shows the plot of the tensile force in the nail due to that mechanism. And as before, if I shorten that down too much, then of course that's going to become a rather ineffectual nail, and we will revert back to our original type of failure mode, which will come out to around about 1.63. It's changed slightly because adding that nail has slightly changed the distribution of nodes in the problem. Okay, so that pretty well wraps up what I've got time to look through in the slope stability. Hopefully that's given you an illustration of what the software can do and the flexibility of the software. So in summary, what I hope you've seen is that discontinuity layout optimization is as straightforward as using the method of slices, but there's no need to specify entry-exit points or solution method, whether it's Jambu or bishops or whatever. You don't need to worry about inter-slice forces or a search space. The software will just seek out the critical collapse mechanism. And as illustrated on the right here, we've actually got a mechanism here where you were just squeezing a soft clay layer, and that would be very difficult to capture with a single circular or even planar slip surface. So every time you solve, the method will automatically search all possible failure modes, and it will find the critical slip surface even if that's highly non-circular. And I hope you've seen, as I've used the software, that the software provides a flexible slope geometry and load definition that you can model retaining walls or piles, equivalent piles or reinforcement. We've got built-in wizards for quick definition of problems. We've looked specifically at the slope one. It's very easy to apply partial factors. We can add in water tables, and you've got the facility to put in RU coefficients if required. and you get comprehensive report output. So just to wrap up, hopefully you've seen the benefits of the software are that it's very interactive, it's solved very quickly, so many of our customers use it very interactively to answer what-if type questions, to explore a problem, look at what parameters significantly affect the problem, what don't, maybe to do some back analysis. So it basically empowers you to get a better feel for the problem. And that one piece of software can solve any ultimate limit state problem type. You don't need to put in any idealizations or correction factors for non-standard geometries, and there's no need to learn how to use many different programs. So I'll finish there, and if you have any questions, please feel free to post them on the via the system. Okay, so I've got some questions coming through. How do we check if the sheet pile provided sufficient strength and embedment? So in terms of embedment, it's a matter, as I showed, of just you can change the length, drag that down, up and down until you get the factor on strength that you wish. In terms of sufficient strength, the software has let's see if I could go back to that particular example. That wall, if I click on the wall, I didn't have time to go into this, but you can actually specify a plastic moment of resistance for the wall. So if that is too low, I'll set that ridiculously low to 1, and we solve the problem. The software will simply cause a failure mechanism where that sheet pile wall bends. So you can put those, you can determine what sort of bending strength is required to avoid a ULS. And do remember this is a ULS software, so that's required for ULS. You do need to check SLS as well. Okay, so that's that question. And it's the same issue for the soil nail. Again, you can change the length of that. So if I revert that strength back to a very large number, as I said, if you want to check you've got the right embedment, you can just change the length as in that way, and check to see whether that has the effect that you want on the actual failure mode. I've got a question about the soil nail. Again, we didn't have time to look into that, but the software models that in a way that allows failure mechanisms to pass through it. So for a sheet pile wall, failure mechanism cannot go through it, but with a soil nail, the failure mechanism can, if you like, go past it, but it can still model the interaction of the soil with a soil nail. And the transmission of tensile forces along the nail. So in the particular properties that you specify here in the pull-out factors, these are actually specified per meter width into the diagram and per meter length of nail. So if you have a row of nails, if you've got one nail every meter, then you need to put in the properties that are relevant to one nail. If you've got a nail every 2 meters, then you need to put in the properties effectively of half a nail, because the software wants to see that in terms of capacity per nail. Excuse me. Another question concerning, let me just go through that. How do we model support conditions? So effectively in this problem we have boundaries, and if I click on a boundary, its properties appear up on the right, and we have support type. So we can choose a free boundary, a symmetry boundary, a fixed boundary. So a free boundary is just a gap. So if I try and solve this problem, I've just basically got a void underneath the soil there, and what's going to happen is the soil is just going to fall out, I suspect, if we reduce the strength sufficiently. Going to get there eventually. It's a kind of unusual problem to throw at it. Yeah, didn't like that one. What I can do is change to what we call a factor load mode, and we've got true on there. Basically what we're asking the software is how much heavier does this soil have to be to cause collapse, and basically it's just falling into that void. So we can change the properties to free or fixed. A symmetry boundary is effectively a fixed boundary, but it's frictionless. But you can use that to model symmetry conditions, for example, for a foundation or for other type of problem. Okay, I have a question. Do we have any plans to include modeling of progressive failure? And if so, what input information would we require? Essentially, the software, because it's based on the theorems of plasticity, it is designed to analyze the ultimate limit state. So it will, its power is its ability to go straight to the collapse mode using optimization, whereas in finite elements, you would have to increment up to that stage. So because it does that, it's not able to actually model deformations and therefore deal with progressive deformation. We are looking at large strain or large deformation type mechanism problems and being able to model those, but that's some way off in those terms. Okay, I've got a question about how we solve seismic problems. So let me just go back to the simple problem. We can, if we go to factor load mode here, and I'm going to, in factor load mode, we can actually ask the software a question: how much heavier does this soil have to be to cause collapse? And in this case, the soil, because it's a frictional soil, it's actually, the slope is shallow enough that it doesn't matter how much we increase the weight of the soil, it will never collapse, and we get what we call a locked solution. But if I remove that, I can actually click here and look at seismic action. So what I can do is apply a horizontal acceleration or a vertical acceleration. And I can either apply those as fixed accelerations, or I can ask the software, what I'll do is I'll do that, how much horizontal acceleration would we require to cause collapse? And I basically set the adequacy factor to true on this, and what that means is the software will apply a nominal unit horizontal acceleration, but the answer I get out from the software will be the multiplier on that will cause collapse. So effectively it will be the horizontal acceleration required for collapse. If I click solve, we get a particular collapse mechanism. You'll see it touches a boundary, so it's not actually valid, but this number here is 1.85. So that actually means that this slope would require a horizontal acceleration of 1.85 g to collapse, which is obviously quite high, and therefore this slope is quite stable. But you can use the software to explore the effect of seismic actions. So the analysis is a pseudostatic analysis, but it allows you to vary the horizontal and vertical accelerations on the entire soil body. So anything with mass will get a body force horizontally or vertically according to these seismic forces. Okay, well, that's just brought us up to 10 o'clock, so I'm going to finish there. So thank you very much for listening, I hope you found it informative. If you're current users, I hope you learned something new about the software that maybe you didn't know. If the webinar has prompted any questions, please do get in touch via telephone or by emailing support@LimitState.com, and we'll be happy to help. If you aren't current users of LimitStateGEO, we'll be in touch over the next few days to get some feedback and see if you've got any other further questions. There will be more further webinars in future covering the whole LimitState product range, so different types of use for LimitStateGEO and also for LimitState Ring and for the LimitState Slab. So do have a look out for those. Those will get sent out by email, but you can also find them on our website at LimitState.com/events. So again, thank you all for taking the time to join us, and hopefully you'll join us again for one of the future sessions. Thank you.